Today I'm going to talk about an inverter I made months ago and it is still working. It is made using discrete transistors, no board, just wires, and here's the schematic for it and I will talk about it later. It uses an SMPS for now because I don't have lead acid battery. I had lithium ion battery but I discharged it because I purchased new batch of lithium ion battery and a BMS, and it was pre-charged by the manufacturer, and I just came home and turned the circuit on and it worked for some time, like some hours, and then basically the BMS turned the circuit off because the battery discharged. It is a 14-volt battery and it needs a 16 volts adapter, 16.8 volts, and I have 19 volts and 14 volts adapter, so that's not going to charge the battery. It needs a constant current and constant voltage. But anyways, this inverter uses iron transformer. It is already resting here. It is 12012 transformer. I'm using a boost converter and you can see the inductor for it on some SMPS power supply core. It should be a very tight core, otherwise it will vibrate and basically it may not boost the voltage much. You need a very thick wire to bind it, and you need 3 MOSFET. It can be Z44N, any P channel, N channel MOSFET. I'm using 110 volts, maybe 50, 60, 70 volts MOSFET, and I'm using BJT transistors here, BC547 and 2N3904 transistors. And let's turn the circuit on and hope for no explosion. It turned on and you can see the motor is running here. The motor is running at 175 Hertz. I turned it off and I will run it on mains. And this is a very dangerous extension board which you should not buy, but I did buy it for some reason. And here you can see how the motor runs. It is slow here, 50 Hertz, quite slow. This motor is meant to run at 50 Hertz, not 175 Hertz. So you need a triple VF compatible motor. There are some motors which are very expensive to buy and they are triple VF compatible. This is a kind of an inverter and you can control the current, voltage and frequency at the output. So it is like a VFD or a triple VF inverter here. So now, for easy understanding, there is this MOSFET which is driving this transformer in half bridge. So now I've connected one of my probe here and one of my probe here, and I can show you the oscilloscope measurement here. And now I will turn on the circuit on, and here you can see, well, the motor is disconnected. It is not meant to be disconnected because the transformer can arc internally and some of the windings will short and it will create some current path and it will destroy the transformer itself. So now I've connected the motor here and I will turn it on. Where it sparked, it sparked where the wires are connected, and here you can see 172 volts peak to peak, and if we switch to peak voltage it is 88 voltage in 1/2 cycle and 88 voltage or 90 voltage at the other cycle. This is because there is a very high resistance in the transformer and you have to compensate for it. At 76 Hertz, and there's torque, and you can see as the frequency decreases the voltage should decrease. So I decreased the voltage, otherwise the motor will burn, because at different frequencies the motor will react differently, because the motor is like an inductor and inductors behave differently with high frequencies and low frequencies. Basically at high frequencies the motor may have high resistance or may have high AC resistance, and at low voltages the motor will have lower lower AC resistance. So that's why the voltage regulation is important. I can decrease it even more at 56 hertz. It is working. I can decrease it even more at 50 hertz. I can again decrease the voltage here by connecting a PWM here. You can see at the positive cycle there is a different, basically this is the negative cycle, this is the positive cycle. So that's how it is modulating it with PWM. It is PWMing now. Basically this is higher PWM thing here. Lower PWM. This is even more duty cycle, and you can see how it changes. This is because of the XOR gate. Well, I wanted to check across this MOSFET. I connected my probe here and ground to the ground, and I was expecting to change the duty cycle by changing the voltage, but actually what happened is that this was already a very high voltage which arced with the potentiometer because this resistor is too low for high voltage. So the trace basically burned and it created a high voltage patch because then because there was low voltage here, this sudden amplifier detected it and increased duty cycle at the basically the gate of the MOSFET, and it increased the voltage here, basically further increasing this resistor, and that is basically like a positive loop. So now I have connected my burnt potentiometer to function generator, and here you can see how it should be functioning. Well, you can see here this is at the maximum, this is at the maximum, this is where the signal is coming like this. Here there's nothing, and then basically this is what was happening with the circuit. So it could destroy the MOSFET and other circuits too, but the great thing is that there are capacitors here to slow down the changes here. Here there is some capacitors here which acts as low pass filter. So the gate of the MOSFET sees something like this, not like this, like some increased voltage duty cycle, decreased voltage duty cycle. This is the crudest way to drive a MOSFET, very crude. It will burn the MOSFET, and when you use a low pass filter here, you will get a smooth basically waveform here, but then the changes of the voltage here will be slower because of the low pass filter here. Now I will test a good potentiometer here. You can see the 1 kHz signal, sawtooth or triangular signal. This is how it should be acting. Nice and variable. So now I will replace this resistor here to 1 kilo ohm, and I will replace this potentiometer. Well, I have changed this resistor to 1 kilo ohm and 10 kilo ohm potentiometer, and now it should be working. Here you can see the duty cycle. Now it is working perfectly, 33 or 29% duty cycle, and I should be able to increase the voltage a bit, but the voltage cannot be increased much. Then let's try to replace it with 600 ohms potentiometer here, 600 ohms resistor here. Well, I have this weird looking resistor here which claims to be 680 ohms, It is close to it, 666. So it is testing time. I have replaced the resistor here. Well, seems like it is working. It is working. Well, I've probed here. Now I want to probe at the gate. Now here you can see the gate voltage or the voltage at the gate. It should be 16 volts peak to peak. Not that much fast rising and falling edge, but it is fine. You can see basically the duty cycle here is again wrong. This is the right duty cycle, 38%, because here the MOSFET is on, here it is not on, and increasing or decreasing the voltage should change the thing here, should change the duty cycle here. I will measure at the smoothing capacitor after the diode, because there most of the problems starts to appear. Well, here you can see there's something here. When I increase the voltage, you can see it increases too. Well, I can turn off the F50 and you can see that there is this 300 volts 300 hertz signal here, basically increasing and decreasing. This is because of the basically switching of the transformer. This is the switching of the transformer, and because there is a low pass filter here, and here you can see the low pass filter. So that's why only DC or low frequency is passed, not the high frequency signal is passed. And if I go to AC, I can also see the switching signal here. I can also see the switching. Can you see the switching here? That's the problem here. You can see that there is high switching, then there is this thing which keeps discharging and charging the capacitor. Well, it is more than 20 volts. It is 22 volts. So now this is high voltage, high interference. Can I measure it now? 30 volts. Well, now let's talk about the circuit. The circuit is very simple. There are two regulators here. This one is a 5 volt regulator. It uses TL431 reference to basically output 5 volts here. Then this 5 volt is taken as a reference, and this regulator takes the reference of 5 volt and output 16 volts. This 5 volt, this regulated 5 volt is given to this oscillator. This oscillator generates the base frequency, which basically is the rotating speed of the rotor. So basically this generates a square wave. It is given to one input of the XOR gate. This is the XOR gate. So this input is taken into the first input of the XOR gate. Then there is another oscillator. This one is a 5 volt triangular wave oscillator. This generates a triangular signal. This triangular signal is given to another comparator here. This comparator can compare the voltage on the potentiometer with this triangular wave. This creates a PWM signal, basically a switching signal. This is high frequency than this. This can go from 20 Hz to 175 Hz. with the resistor and the capacitor value. This one can go up to 2.2 kilohertz. So basically if this oscillator outputs a 1, so basically if the duty cycle is here 60%, it will invert it and it will basically go 40%. So that's how the polarity thing is working. So basically you are switching it and you are basically regulating the voltage. This XOR gate creates some another signal here which goes into the NOT gate. This NOT gate drives this MOSFET and the output of this NOT gate is taken into another NOT gate. So basically when this transistor is off, this one is on, and when this one is on, this one is off. So basically if the XOR gate outputs a 1, so basically this MOSFET will be off because the voltage here will be 0, and this will be high because the voltage here will be 1. So basically that's how it is switching with PWM and the base frequency. This 16 volt regulator is very important because the MOSFET can take up to 20 volts. 16 volts is the sweet spot for the MOSFET to basically switch on fully. So you are giving your 16 volts to this NOT gate circuits here. This transistor needs to be a bigger transistor and it needs to be mounted on a heat sink because it will be handling up to 30 volts as you saw in the test. This one is a boost converter. You can see that there is some triangular wave oscillator here similar to this circuit. Then there is this comparator thing similar to this circuit. Then there is this error amplifier. This basically compares 2.5 volts to the input signal here with the 10 kilo ohm potentiometer and 680 ohms resistor here. Basically if the voltage here is 2.5 volt, then it will not change the duty cycle. If the duty cycle is something like 10%, if the voltage here is higher, the duty cycle will basically be lower. It can be like 9% or 8%. If the voltage here is lower, then the duty cycle can be higher, like 11 to 12%. You need to pass this through some capacitors because then it acts as a low pass filter, basically filtering some voltage here, filtering the 2.5 volt again to basically output a clean voltage here, which is again basically smooth by adding a capacitor here, then a resistor and another capacitor. So this acts as a low pass filter. This is very important because if the changes are very fast like this, then what will happen is that this comparator will output something like this, which is like garbage. It can destroy the MOSFET, it will blow out. Basically filtering it, it will output a steady voltage here, which will create a nice duty cycle or PWM signal, which will switch this MOSFET and create high voltage here. So that's how it is working. It is very simple, and the idea of this thing is taken by this simple circuit. I was experimenting this with this circuit as a kit. I used some high value capacitor here, some 10 kilo ohm resistor here. This is a multi vibrator circuit. It creates a basically square wave signal which can drive the MOSFET here, and with some Farad transformer you can generate some voltage here. You can generate some current too. So I used to generate some current, and then one day I thought I should make a inverter here, triple VF inverter. So I made this circuit and implemented it, and it is a single phase triple VF inverter because you can basically set this circuit to 30 volts here. So the center tap of the transformer will receive 30 volts. This will regulate 16 volts. So basically everything is like stabilized. So you can basically control the voltage by using this potentiometer knob. The higher the knob, the more voltage goes into the transformer. The lower the knob, the lower voltage goes into the transformer. So that's how it is working, and thanks for watching the video. I hope you liked it, and I hope you liked my explanations too.